Okay, so what can we use for this chemical potential? Could we use enthalpy? So enthalpy is the heat at a constant pressure. This is ironic because I just lectured about this in Chem 1A yesterday. So heat at constant pressure is related to the change in internal energy. But enthalpy here doesn't really help us out because enthalpy predicts that all exothermic reactions are spontaneous and all endothermic reactions are not spontaneous. This is not true. What's an endothermic reaction that is spontaneous? Freezing is actually exothermic. Burning is exothermic. Burning is exothermic, yeah. Ice melting. Ice melting is an endothermic reaction that is spontaneous, right? So enthalpy doesn't help us out. Another one would be those like chemical ice packs in a first aid kit. You know, you break the seal and you squish them around and it gets cold. Endothermic reaction, and it's spontaneous. Did it again. I should really just read the slides. So consider the following spontaneous processes that involve an increase in enthalpy. So if you're melting ice above the freezing point, you're increasing the enthalpy of the substance. It's taking in energy. Evaporation of liquid water to gaseous water, that's an endothermic process. Dissolving sodium chloride, also an endothermic process. But what's happening in all of these things, all of these processes? Let's look at here, we've got our water. Here's our solid water molecules, right? They're literally frozen, right? They can't move around. And when they melt now, they're moving around. We have an increase in entropy in all of these processes. So let's look at entropy as a possible stand-in for our chemical potential. So in each of those processes, we just looked at the ice melting. Here is water evaporating, and here is sodium chloride dissolving. In each process, the disorder or randomness of the system increases. So entropy is a criteria for spontaneity. So informally, we think of it as an increase in disorder or an increase in randomness. Think of, maybe that's on the next slide. No, it isn't. Okay. In the fall, the trees, the leaves fall, right? The leaves fall in the fall. They were very organized when they were on the tree, right? If you've studied botany, the trees are very organized in how their leaves are attached, right? And what happens when they fall? Do they fall in neat little stacks? No, they blow all the heck over the place, right? Very, very random, very messy, big increase in entropy, in disorder. So entropy is a thermodynamic function. This is the not simple explanation of entropy. It's a function that increases with the number of energetically equivalent ways to arrange the components of a system to achieve a particular state. That's not going to make sense yet. There's an equation for entropy. Entropy is a capital S, don't know why. Capital S is equal to a constant, it's called the Boltzmann constant, times the natural log of W, where W is the number of energetically equivalent ways to arrange the pieces of that system. So the units of entropy end up being joules per Kelvin. So let's imagine a fixed amount of an ideal gas, and the pressure, the volume, and the temperature are going to be constant. The state, or we could think of it as the macro state of that system, is defined by the pressure, the volume, and the temperature. The energy of the system is constant. But exactly where the energy is at any given instant is anything but constant. Because what are those gas molecules doing? They are zinging around, they're traveling in straight lines till they run into something and they're bouncing off, right? Each particle has kinetic energy. At any one instant, a particular particle could have high kinetic energy, but after a collision with somebody else, it might have low kinetic energy. And so we have the arrangement of energy shifting. So a microstate would be the exact internal energy distribution among the particles at any one instant. So like taking a snapshot of where all of the atoms are and what their energies are. So a given macrostate can exist as a large number of different microstates. So you could have that sample of gas, same pressure, volume, temperature, number of moles, but at any given time, exactly where the molecules are and exactly where the energy of those molecules is going to be different. This is constantly changing. And so there's like a gazillion different ways to have that arranged. So that W is essentially the number of possible microstates that would result in a given macrostate. So let's take it down from, Avogadro's number of particles to 2 particles. So here we've got 2 systems, A and B. Each system has 2 particles with a total energy of 4 joules. The macro state of each of these is the same. 2 particles, total energy of 4 joules. System A has only 1 level of energy. Both of the particles are at 2 joules. But system B has 2 different energy levels, 3 joules and 1 joule. And so you can have this microstate where the red one is at energy equals 3 joules and the blue one is at 1 joule. Or you could have the blue one at 3 joules and the red one at 1 joule. Do you see how these 2 are different in terms of who's got the energy, right? Who has more, the red one or the blue one? Those are different, and yet the overall macro state, 2 particles, 4 joules of energy, is the same. So system B has greater entropy because it has 2 different ways to arrange the energy, whereas system A only has 1 way. Does that make sense? Entropy is a very confusing thing. Yes. All of it? The microstates? Okay. So if we look at these kind of from a distance, a macro perspective, right, they are the same in that they both have 2 particles and they both contain 4 joules of energy. For this state, the only possible arrangement is that each of the particles has 2 joules of energy. So at any given time, you got those 2 particles, they each have 2 joules of energy. But here, there are 2 different possibilities. And so then we have 2 different microstates that are possible. You could have the red one at 3 joules, or you could have the blue one at 3 joules. It's like, which of the kids gets to ride shotgun? The total energy is the same. The total energy of this is 4 joules. The total energy of this is 4 joules. The total energy of that is 4 joules. From the macro level, it's the same.
Okay, so if I were to have, just an example, 20 joules,
Mm-hmm.
and system A was 10 each,
Mm-hmm.
and E would be 15.
if you start adding more particles in here, then you get like exponentially greater numbers of arrangements.
Okay, but as long as it stays within 20.
Yeah, as long as it stays within the same amount of energy, it's the same macro state.
Okay.
It's like probability of which.
Yeah, it is related to probability. And my mind is thinking about the minivan and the different arrangements of the 5 children that would fit in the minivan at one time and who got to sit where, right? Lots of different combinations, lots of entropy, lots of messiness
Even more
in the minivan.
combinations when they get their driver's license.
Yeah, but then I don't have to look at it. So the entropy of a state increases with the number of energetically equivalent ways to arrange the components. We can also think of this as the state with the highest entropy is going to have the greatest dispersal of energy, or the energy is going to be more spread out. So energy of system B there was 2 levels. So the energy was spread over 2 levels, whereas system A, all the energy was in 1 level. So if we have energy that's highly dispersed or highly randomized, that's going to have more entropy than a state with the same energy that's highly concentrated. So you think about the leaves on the tree, right? They don't really seem concentrated, but they're all on the tree, right? What happens when they fall off? They go all over the place, right? They blow down the block. They're spreading out, right? Definitely more entropy there. So the second law of thermodynamics is that for any spontaneous process, the entropy of the universe increases. Not necessarily the system, but the entropy of the universe. Okay, that's what spontaneity depends on. So entropy is a state function. Remember those? The state function depends only on the state of the system, not how it got there. It's like elevation is a state function. You go from the bottom of a mountain to the top of a mountain. The change in elevation is the same regardless of how you got there, if you hiked up or you took a helicopter. The distance you travel, even the energy you expended, would be different, but the change in elevation is the same, doesn't matter how you got there. Entropy is like that as well. So the change in entropy is just the final entropy minus the initial entropy, and what happened in the middle doesn't matter. So here's a slightly more complicated system. Here we have a gas, and there's 4 particles, right? And on this side is a vacuum. And how do you know that's a vacuum? Because there aren't any gas particles over there. Because if the gas particles are this big, we'd be able to see the air too, right? There's literally nothing there. So the gas expanding into this vacuum over here is not expanding against a pressure. Remember pressure volume work? The pressure times the change in volume is equal to work. So the work is 0. The total energy of this system doesn't change when some of these guys go over here. But the entropy does, because now they are spreading out. So we open that stopcock. Here's the open stopcock. And there are several different microstates that are possible. We could have all 4 particles on the left. We could have all 4 particles on the right. We could have 2 particles on the left and 2 particles on the right. And then for each of those, I misspoke, each of those is a macrostate. For each of those, there are possible microstates. Well, for this one, just considering sides, there's really only one microstate. We got all 4 particles over here. And for this one, we got all 4 particles over there, and that's it. But here we've got 2 on each side. Well, if these guys are A, B, C, and D, there's different possibilities, right? Where you still have 2 on each side. So the macrostate here only has 1 microstate. All 4 of these are in the same place. State B only has 1 microstate. But state C has 6 microstates. So we could have 1 and 2 versus 3 and 4. Here we have the opposite of that, 3 and 4 versus 1 and 2. We have all these different combinations. So the probability of finding atoms in state C is 6 times greater than in state A or B because the entropy is 6 times larger. There are 6 times as many microstates. Do you see why that's different? Why these 6 things are different from each other? If you've ever been in a group of people, maybe going to a concert or something and you've got these tickets and they weren't assigned to a particular person, well, which people are going to sit in the front row and which people are going to sit in the row behind them and what order you're going to sit in, right? It matters to people. And there's different combinations that are possible. Any questions? If you increase the number of atoms from 4 to 20, now you get 184,756 microstates for state C, where you have an equal number of atoms on each side. But the number of microstates for A and B stay the same. Each has 1. So the change in entropy going from state A to state C is positive because the final entropy is larger than the initial entropy. So is that gas going to spread out and expand into the whole thing? Yeah, it is. When the atoms are confined to just one side, their energy is confined. When they're evenly distributed, then their energy is dispersed over a greater volume. Dispersal of energy is greater entropy. So the second law helps us to explain some things that the first law doesn't. So here we got ice water. We've got heat traveling from the water to the ice, right? So the water is giving heat to the ice. The ice is not giving heat to the water. The first law of thermodynamics does not prohibit the ice from becoming colder and the water from getting warmer. That'd be weird, huh? You put some ice in a glass and you wait a little while and those ice cubes have gotten super cold and now the water's boiling? That doesn't happen, right? First law of thermodynamics doesn't say that that can't happen, but the second law says energy is dispersed, not concentrated. And so here, the energy from the water here spreading into the ice cubes is going to be less concentrated, more dispersed. And then we also have entropy involved in the changing of states. So we think of a gas is not organized, right? Those particles are just literally all over the place. Whereas in a solid, the particles have some sort of, even if it's a random order, they're stuck there, right? They can wiggle, but they can't move around, like you guys right now, right? You're shifting, everybody, I think, is breathing. Most people have their eyes open, so that's good. When ice melts into a liquid, now the particles can move around. We have more possible microstates, right?
Like lab.
Yeah, that's like lab. So lecture is the solid state of students, and lab is the liquid state of students, and the gas is when class is over, and everybody effuses out the door, and it goes their separate ways. That's why it takes so much energy to get everybody back in here concentrated, right? gases have more ways to distribute the energy. So not only just moving around, but gas molecules can rotate. They can spin around, and they can have translational motion. Right? In a solid, vibrating is about the only thing they can do. They can't even spin around. They're stuck. Right? So the gas has more places to put the energy, and so it has more microstates and more entropy. Does that make sense? So entropy increases for each of these things. If we go from a solid to a liquid, or from a solid to a gas, or from a liquid to a gas, the entropy increases. It's less ordered. If we increase the number of moles of a gas during a chemical reaction, now we have more gas, and gas has more entropy, so that will also be a positive change in entropy. So predict the sign of delta S. So here we have H2O in the gas state going to H2O in the liquid state. Delta S positive or negative?
Negative.
Negative. It's becoming more ordered. Entropy is decreasing. Solid carbon dioxide sublimes.
Positive.
That one's going to be positive. It's going from the solid state directly to the gas state. What about this thing here?
Positive. It's maybe
Positive.
4 moles.
So started with 2 moles of gas, now we have 3 moles of gas. 3 moles of gas have more places to put their energy, and so this is also positive. Any questions?